OK, that's close enough. Let's crack on. This is like, so I've got 40 minutes for this. It's also been a half-day workshop, and it is also the first day of a 2-day workshop. So there's a lot to get in, so I'm not going to run all the code samples. We're just going to dip in and out of stuff. But yeah, so everyone .NET developers? Yeah, that would make sense. This is mostly a .NET conference, isn't it? Because I was at Øredev in 2013 and 2014, and then I haven't been back, and they've moved it. This is a completely different venue. It used to be kind of in central Malmo. Yes. Also, I got very drunk one night at an Øredev, and Greg Young dislocated my shoulder. So yeah, if you're into CQRS, there you go. So, this is an important question, and the main reason it's important, obviously you're in this room because you think it's important. The problem is, how do you go to your business and convince them that it's important to spend that extra time to enhance performance as much as possible? And I kind of break it down to these 4 things. So you've got the user perception of your system. Users notoriously have incredibly short attention spans, and if things take more than 0.2 of a second, they're gone. They're off on YouTube or TikTok or whatever. But yes, user perception of your system and how useful it is. If it takes a minute to run a query, then they're going to go, this is rubbish. If it takes a second to run a query, they'll probably be like, that's very clever. So there's that. The competitive advantage is a big deal in things like finance, trading systems, anything where the performance... I said I wasn't going to move to the poor video guy, and I'm just kind of like just side to side like this. I'm going to try and stay still. But yes, if you are trying to do something and lots of other people are trying to do that thing at the same time, then if you can do it faster, then that gives you an advantage over those people. And then there's a very simple one, infrastructure costs. So if you can build something that uses little memory, and if you're coding for performance, generally that involves using fewer CPU cycles, because that's really, there's 2 ways to do performance. One is clever CPU instructions, which is great if you're programming in assembler. The other is just try and do as little as possible. That's mostly what we're going to be looking at here. And that keeps your infrastructure costs down. That means that you can run on like T2 micros or D1 machines in Azure or anything like that. And you can have much more dense compute costs, and that keeps your costs of infrastructure down. If you make something 10 times more efficient and 10 times faster, then theoretically you can run it on 1/10 of the infrastructure, and that is a meaningful cost saving to the business. And then there's just the environment. So I haven't got the most recent chart, but we're at something like 20% of the carbon footprint of the world is us. Just burning CPU cycles, running React front ends, and Node.js or Ruby backends, which are just hideously inefficient. And so if we can get to a point where everything we write runs on a Raspberry Pi, and we can just stick it in our house, then we're going to be a lot friendlier to the environment. So I'm hanging this talk off the 1 billion row challenge. Who's seen or heard of the 1 billion row challenge? Few people. For those who haven't, this was a thing, it was a Java developer who started it. And it is essentially, you have a UTF-8 text file. That's important. We'll come back to that. It has 1 billion lines or 1 billion rows separated by just the new line character, so Unix. And each line has the weather station name and a temperature separated by a semicolon. And the challenge is to calculate the minimum, maximum, and mean temperature for each of those weather stations and display it on the console output and exit, and do it fast. So that's what the data looks like. And we start off with the naive implementation. So we're .NET developers, and we have strings and we like our strings. So yes, this is the naive implementation. We use file.openText, which gives us back a stream reader, and stream reader reads a line of text at a time from the stream and turns it into a .NET string and gives us that back. And then when we want to tokenize a line, if we are not worried about performance, we call line.split. And that returns us an array with lots of new strings, and we can then work on those individually. So our key is the first part. That's the weather station name. And then we have our second part, which is our float. Sorry, the other thing that's important to notice here about the temperatures, they can be negative, but they always have 3 decimal places of precision. That's a dot for the decimal separator because I'm English and that's what we use. You may be more used to commas, but trust me, that's the decimal. So yes, weird people with your commas. Who's comma people? Oh my God. That's how you separate like million bits from 1,000 bits and everything else. It's just confusing. So yes, so we do that, and then we get our counter out of a dictionary, which we're using the name of the weather station for, and then we just write all of that. And so I am just going to go into src and baseline, and we will do .NET build. So yes, this is a key sort of starting point, is that we always want to do the release build. So when you do a .NET run, it defaults to running in debug mode, which means it's got a whole load of extra stuff in the assembly, and it's doing a whole bunch of extra stuff while you're running it, just so that you can attach a debugger and say, what's the value of that variable? When we're trying to make something run fast, we don't want to do that. We just want to strip as much of that stuff as possible out, do all the optimizations and everything that debug builds don't have, and then run that. So I can say .NET run -c release, and then -- and oh no, hang on, we'll do the no build, and then we will do billion.txt. And this is going to take a while to run. And part of that is probably because it's writing lines out to the console. But these are millions ticking up here. And so you can see that this is taking a while to run. And while it does that, I will talk about why it's taking a while to run. So the primary thing that is happening here is allocations, heap allocations. So we are creating a string for every line that we read from the file. So that's one allocation. And then we do our line.split. And that creates a 2-element array of strings. So that's an allocation. And then it creates those 2 strings. So that's 4 allocations per line. And then multiply that by 1 billion. So 4 billion allocations. And we have a garbage collector that is watching our allocations and going, I need to clean that up, I need to clean that up. And so every now and then, the garbage collector just goes, everybody stop what you're doing, and cleans up a bunch of strings that we've allocated. And so this is why when you see a lot of the work that Microsoft are doing, there's that guy Ben Adams, who is almost solely personally responsible for Kestrel being up at the top of the TechEmpower plain text benchmarks, because he's done some ridiculous things. But so much of it is just about avoiding allocations. So using value types and not using line.split and creating loads of arrays, and just looking for better ways to do these things. We are 3/4 of the way there. So yes, this is what a lot of .NET performance work has been doing. And it's interesting comparing that to other languages. So if you look at Java, for example, Java has no concept of reference types and value types. It just has reference types. Go also only has reference types, but they can be allocated on the stack. You can say, create this on the stack. And I know that's something that the .NET team are actually looking at doing. There you go, 2 minutes, 27 seconds to process 1 billion rows of data. That's not very good. And my day job, I do consulting, and I do a lot of performance consulting. And this is a very good sort of representative idea of some of the challenges that people call me in to help them with, because they go, we get 1 million rows a minute coming in a text file from some external service, and it's taking a minute to process it, or it's taking 1 minute and 10 seconds to process it. How can we make it faster? Go away, console. So, optimization essentially involves doing less with your code. The less you can do, and this includes all the side effects of your code as well, like allocations and so forth. And so the first thing to think about here is that this file is UTF-8. And UTF-8 is a fantastic encoding, because if a character is in the 7-bit part of the ASCII table, so the bit where the leading digit is a 0, then it just uses a single byte. Now, there are city names in there that do not. They contain characters with umlauts and accents and cedillas and all those sort of things. But for the most part, we know it's just ASCII, and we can use that to cheat. For example, we know that the float part of the line, that's ASCII, because negative, dot, minus sign, dot, and the digits are all in that lower bit of the ASCII table. We also know that it's using a single new line character to break on, which means we can just look for that new line character. And we know that if we find a byte that is equal to 10, that is new line, because any byte that is part of a multi-byte encoding, the leading digit is 1. So we can use this to cheat. So let's jump into the code again and see if I can find the right bits. And so we have ucollapse. There we go. UTF-8 stream. So yeah, here we have a version of this that doesn't use strings, except you can see there it has a dictionary of string and counter. But we create a byte array, and technically I could use stack alloc here. 128 bytes is the kind of thing you would put on the stack, but it doesn't really give us an advantage, because that's a single array. We're creating it once, it will live for as long as the process lives, and then it will go away. And so I'm just using an array there. And then we just call stream.read, and we say read into bytes, starting at 0 and going to 128. If we haven't read anything, that means we're at the end, so we break. And then we can just look for new line in the array. And if it doesn't find new line, then it will say I'm on the last part of this. Otherwise, if it's 0, it jumps across to the next bit there and does the process line, and then go from wherever we were back to here, and then come back to the start and read the next 128 bytes. Because that 128 bytes might include 2 lines. But most likely it will contain the start. It'll contain one line and then the start of the next line. So I've made this jump around the stream. And so this skips quite a lot of the work that the naive implementation is doing. It skips the creation of strings. We're using a span of byte, which in .NET land is essentially our UTF-8 string type at the moment, which is suboptimal, but that's what we have. But it's also skipping that process of taking those UTF-8 bytes and converting them to UTF-16, which is the default internal implementation. And that is a slow process, because what you're essentially doing, UTF-16 uses 2 bytes for every character. And so you have your just single byte thing over here. You have to allocate essentially twice as much memory and then copy the bytes over and convert them to the correct value for the UTF-16 encoding. So that's work that has to be done as well. So yes, this runs a lot faster. And then we have down here in our process line, we have our read-only span of byte. So this is the type that was added in .NET Core 2.1, I think. This is the point at which .NET started to be competitive in terms of performance, when they added span, read-only span, memory, and read-only memory. And so we can pass our span in here, and then we can find our semicolon in that line, which is also an ASCII character, so we know that's OK. And then we can say the name is the bits up to the semicolon, and the value is the bits from the character after the semicolon to the end of the line. Then we can call float.tryparse. So we are avoiding a lot of the allocations here. We have 1 string allocation per line now, and that is because our dictionary is using the name of the weather station as the key. And so the only way we can say, is this already in the dictionary, is to convert that first chunk of the data to a .NET string and then do a dictionary lookup. But apart from that, it's essentially the same. I'm not going to run this, because if I run all of them, we will run out of time. But that takes it down to about 1.5 minutes. So we save a minute just by skipping all those allocations and working directly against UTF-8 bytes. When you are doing this sort of thing, there are lots of ways to measure performance. And the one that people seem to default to, in my experience, is they use profiling tools like .trace and .memory, or whatever the hell's built into Visual Studio these days. I don't know, I don't use Visual Studio. Or Ants Profiler, if your company has enough money to hemorrhage in the direction of red thing. God, my brain is going. Anyway. But it's very, very difficult to get useful information out of profiling tools. And the problem is that they're stupid. They measure everything. They are measuring every single thing that your program is doing. And if what you care about is finding the things that are slow, then that can be helpful. But if what you care about is making those things faster, then what you want is a tool that lets you compare very, very small chunks of code, basically compare algorithms. And so for that, we have BenchmarkDotNet. Brilliant open source NuGet package, and we can put all sorts of stuff into BenchmarkDotNet. So what it does, it takes a method that you've decorated. It's a bit like a unit testing, but you put benchmark on there. And it runs that method, and it runs it a few times to get a rough idea of how long it takes. And then it runs it as many times as it can. It just loops it just to really stress test it. And then it tells you your iteration time for each of the methods. It will also tell you how much memory was allocated and how many allocations were performed on the different heaps, and so it'll show you Gen 0 allocations, Gen 1 allocations, and you can also get it to output both the intermediate language, so the language that was generated from the C# code, the bytecode, and the assembly language, which is what the JIT has generated to run on the CPU. And that's really interesting. Who speaks assembler? No. I mean, Z80, yeah, a bit of 6502, but whatever the hell we're on now, AMD X64, no, I do not speak that assembler. So this is the only use that I personally have found for all these AI coding assistants. I use JetBrains, so I've used JetBrains AI Assistant, but also Pieces, which is a thing that's currently burning VC money and is completely free, pieces.app. But yes, you highlight the assembly code, or you copy and paste the assembly code, and you say to the AI, what the hell is this doing? And it goes through it instruction by instruction and actually explains it to you. It is really useful. Because without that, I just look at it and I go, you've got quite a lot of MOVs in there, and there's some LDAs, and ooh, that's an SSE instruction. So yeah. But essentially what we do with BenchmarkDotNet is we go, OK, here's 3 lines of code from my application. I'm going to put those into here, and then I'm going to spin a few other possible implementations, and we will see how we go with that. So, UTF-8 cheat mode. Benchmarks, benchmarks, benchmarks. Parsing benchmarks. Nope, not you. Key hash benchmarks. OK, so yes, because what we have, apart from a complete inability to work my computer, right, that city name, that string that we're creating there, I know allocations are bad, and I know a billion allocations are not ideal, and so I want to avoid those if possible. And so if we start to think about what that data actually is in terms of how it's represented in the computer memory, it is a chunk of memory that we have been given, and it's got some bytes in it. And how .NET sees those bytes is entirely down to the compiler and the .NET runtime, and so we have said this is a string of bytes, and we're representing it as a span. And then we can just force the language, we can force the runtime to see it as a different thing, because 8 bytes could also be a 64-bit integer. And if we cheat a little bit with this for simplification purposes, that means that instead of creating a string with all the characters from the name, we can look through our weather station names and say, are there any weather stations where the first 8 characters are the same? And we can find those, and there was Alexandra and Alexandria. And so I deleted Alexandria from the thing that generates the test data, and everything else is unique. So we only need those first 8 bytes to uniquely identify the weather station name. And so we can look at different ways of generating a key based on this key hash thing here. And so we have 2 ways of doing it. And they are all hidden away in my key hash class here. So we pass in some bytes. This is going to be just everything up to the semicolon. And then we say if we've got at least 8 bytes, then we can call memory_marshal.read. Memory marshal is, it's the place where you go for performance stuff. There's also a class called collections marshal, which does interesting things with lists and dictionaries. So we can just essentially say, give me back those 8 bytes, but as a long, so that the runtime now thinks it is a 64-bit integer. We have a slight issue with that in that if the city name is like London and it only has 6 characters, or Malmo and it only has 5, then we don't want to take the semicolon and the first 2 characters of the temperature, because that's going to give us a lot of Malmos, because they're all going to be different. So what we do here instead is we stack alloc a 8 element byte span. And who has used stack alloc in their code? Yeah. Stack alloc is your friend. Stack alloc, the problem with stack alloc is that when we were on the old crap Windows only, just hideous .NET framework, how did it become successful? I don't know. But if you want, it had stack alloc. C# has had stack alloc, I believe, since version 1.0. But stack alloc used to return a pointer. And if you were returning a pointer, you had to mark your method or that block of code as unsafe. And I know why they called it that, because one of the things with .NET and with garbage collected languages generally is this idea of memory safety. You're not going to have memory leaks. I mean, you can, you don't even have to try that hard, but yeah, just don't dispose your database connections. But yeah, so you have to mark your method as unsafe, and then in order to do that, you had to mark the assembly, the project, as unsafe. And so then you go to your enterprise overlords and they say, oh, no, you can't have unsafe code. And you say, why not? And they go, because it's dangerous, which is another word for unsafe. But yeah, it was, people had problems with it because they're kind of like, you've now got a pointer at some memory and you could just go mad with that. So don't. When they introduced span, and all span is on the inside is a pointer and a length. That's it. That's all it's got. It knows where something is in memory. It knows how long it is. There's stuff going on. So now stack alloc can return a span. And it can return a span of integers or bytes or most value types. And I think in .NET 9 it can return a span of reference types as well, although don't quote me on that, I may be wrong. So yeah, which means it's much easier to use, it's much safer to use. So if you have code where you're allocating a little array to do some stuff, and that array is less than, let's say, 128, or, it's being allocated on the stack. Each thread has a megabyte of stack memory. Is that right? Yeah, I think so. And it doesn't involve an allocation, doesn't involve the heap, doesn't involve the garbage collector, and it's a very nice speed up. So we have that memory marshal way of doing things where we have to allocate this span of bytes. We have to clear that span because it's not guaranteed that it will be zeroed out by stack alloc. Then we can copy our bytes from our parameter into there, and then we can call memory marshal.read alongside that. And then there's the maths-based approach, where we start with our key being 0, and then we go through our span of bytes. Note the interesting for loop thing there. It makes very little difference with span because that gets optimized anyway, but I put it in because if you are doing like for int I equals 0 and then I is less than list.count or dictionary.count or something like that, it will do that property lookup on every loop around the for. And if you want to eliminate like 2 or 3 assembly instructions, then you can cache that value. So we can put 2 assignments at the start of our for loop and then just compare to that. And all we're going to do is shift the bytes across. So we'll copy them to the start and then we'll shift it across a bit and everything will work nicely in there. And this is the sort of thing where you kind of go, oh, and then we have the unsafe version of this, because it's always fun to look at some unsafe code. So yes, if your enterprise lets you use the word dangerous in your code, then we can do this version, which takes a ref to a byte pointer and then does essentially pointer dereferencing and loops through like that. So if we go back to the key hash benchmark, we have with maths and we have with unsafe, and these are our 3 benchmark types and benchmark methods. And we tell BenchmarkDotNet that they are benchmark methods by adding this attribute. And one of the properties you can set is baseline. Baseline equals true. So when you create your benchmark class, you have essentially your naive implementation or whatever your current implementation is. And you have a theory that you've come up with a faster way of doing that thing. And so we put baseline on the original, and then we will see comparisons to that. So it will show the performance of other methods like as a percentage of the baseline. And within here, we have our program.cs, and we've got multiple benchmarks in here. And so there's like a benchmark.run, and you just give it the type name, the class name that you want to run against. But benchmark switcher, and you say, look at the current assembly, find all classes that have any methods decorated with benchmark, and then display them as a list. So if I run this, we do .NET run -c release. And again, benchmark.net, always run it with the release flags. And then we'll just do key hash benchmarks, and we'll see what benchmark.net does for us, because it does a lot. So as it goes through, it's looking at 2 aspects of the code. There's overhead, which is benchmark.net and the .NET runtime and everything. And then there's workload, which is your actual method that is being called. And so the overhead stays fairly constant, but benchmark.net needs to calculate it so it can subtract it and give you an accurate idea of what you are doing. So yes, it also measures with insane precision. So we're looking at microseconds here, nanoseconds for the overhead. But it's worked out roughly how fast the method runs, and so you can get a clue as it's running through. If it's running fewer iterations of a method, then that probably means it's not that good. These seem to be fairly similar at the moment. The other thing it does, so you see the workload warm up. I'm going to assume that's like a beeper's gone and you need to speak to somebody rather than I'm shit. There's a laugh, that'll do. I'm happy again now. Right, yes, so the warm-up bit is important because in .NET these days, we actually have 2-tier JIT. And so when the application first runs, the JIT is doing compilation as fast as possible. Yeah? So you don't want it to be necessarily purely optimal. You want it to start quickly. And if it was doing all those optimizations, that would slow start down. But in about 5 or 6, they added this 2-tier JIT thing. So it JITs the quick version of the method, the one that it does quickly, but then it tags the methods and sees how often they are called. And if you have a method that's called a lot, the JIT actually goes back and says, can I optimize this method better if I take a little more time over it? And if it can, it does, and then it redirects calls to the original, to that one there, and your application actually starts running faster over time. So that's what that workload warm-up is. Run the thing enough times that you force that second tier of JIT compilation and optimization to come into action. And so we can see here that yeah, I haven't really made that much of a difference. Maths appears to be the fastest way to do this. Unsafe, weirdly, is actually slow. So that thing with the pointers, that was slower than the one with the span, which is intuitively wrong. But yeah, so we have shaved off about 50 microseconds by doing those maths things. So that doesn't make a huge amount of difference. I'm running way behind on this. So, okay, let's just jump back into here, and we will look at the other thing that we are doing on all of our lines here. So we have float.tryparse, and that's got sort of error handling and can return false and so forth in there. So one of the things that you can do is just just use float.parse, because you assume that the input has been sanitized, and so they're all going to be valid floats. But I am old enough to remember processors like the Intel 486SX, which didn't have floating point maths, because floating point maths is insanely complicated. The first Pentium chip got them wrong, and Intel had to replace the whole first batch of Pentium chips because it couldn't do long division. So yes, float maths is slower than integer maths. And we know that our input is a digit and then a dot and then 3 digits, and so we can process them all as floats, or we can process them as integers, and then when we get to the point of displaying them to the screen, we can divide by 1,000. And so this was another benchmark that I did, and we will do this again, and then we will run math benchmarks. Ooh, that's American. Yick. So yes, and this does actually make quite a significant difference. Stop, shh, bugger off. My watch is binging Teams messages at me. So yeah, math benchmarks. So all this benchmark is doing, we have an array of 10,000 integers, and we have an array of 10,000 floats, and we have a benchmark to add the floats together, because this is essentially what we're doing per line. And then we have a version where we add integers together. And we can see that the difference we've got there. So this is one of those ones where I knew it was going to be faster. I was surprised it's actually 3 times faster. So integer mathematics, if you can do all your big, complicated, lots of data lines things, treating everything as integers, and then just turn it back into a float at the point where you want to display it to your end user, then it's a lot more efficient. So that's like a 3 times speed up. And this was on one of the things that was the most complicated point on our code. And then we get to the point where I'm just going to talk. So yeah, then you get to the point where, at the moment, we're using a stream, UTF-8 stream of bytes coming off the disk, process them a line at a time. That is very inefficient. There are better ways to get data from files on the disk and into memory, and specifically into the CPU cache. And all operating systems have this concept of a memory-mapped file. And they had, the original use was for inter-process communication. So two processes could both have handles into it and be writing and checking and reading and all this sort of stuff. But you can also just use it as a way to open a file and read it into memory. And it actually uses, it's similar to the virtual memory system, the swap memory system, where it's very, very quick at just copying bytes out of a disk file and into memory. And so if we switch to that, then we get a huge speed up. But the other thing that then gets interesting is that we can then do parallelization, because now, instead of a 17 gigabyte file on disk that we're reading in a chunk at a time, as far as the computer is concerned, as far as the CPU is concerned, we have a 17 gigabyte chunk of memory, and we have pointers into that memory that in the code is wrapped with a span to try and keep things a little bit sane. And so that means that we can parallelize our code and use all our CPU cores, because the single read a stream of stuff and do things one at a time, that's only going to use one of the CPU cores. And I've got 16 CPU cores in this laptop. And so splitting the stuff up, memory mapped read, and so we have an analyzer. We pass in our memory mapped file. This comes from system.io memory mapped files. And then we create a view accessor, and we have our byte pointer, and then we acquire a pointer to this block of memory. And then we can divide the overall size by our thread count, and with thread count you want to set that to environment.processor count, because there's no point having more threads than you have cores in your CPU or CPUs. And then we can work out the rough chunk size, and then we can go to the end of our estimated chunk and just look for the next new line character. That becomes the end of that chunk and the start of the next chunk. And we do that for as many things as we've got, and then we run the code. And it runs approximately 16 times faster. Big surprise. OK. And then we have our unsafe work stealing algorithm, because that version of the thing, it divides the work up into 16 threads, and they all run independently. But if one of them is running slowly for some reason, might be one of those mercurial cores or whatever, then that's going to slow everything else down. And so we have a work stealing algorithm, which basically, as soon as a thread is finished, it can go and look and say, is there anything else for me to do? And theoretically, they will run a lot faster like that. And then, the final part, 40 minutes is not long enough for this, is native ahead-of-time compilation, because the actual 1 billion row challenge is how long does it take to run, and how long does it take to display that stuff to the screen. So that's including launching the program. And we now in .NET have native ahead-of-time compilation. It's limited at the moment, but with every new version of .NET, those limits are reduced. So for example, in .NET 8, you can't use Entity Framework Core with native ahead-of-time compilation, because Entity Framework Core does a lot of runtime code gen, and you can't do that when the JIT's not there. In .NET 9, the EF team have gone through, replaced all that runtime code generation with source generators, and now you can use EF Core with native AOT. So I'm just going to jump back to my window here. We're going to do src, and we're going to go to native 1BRC, and we're going to do .NET build -c release. Actually, we can do this. Right, so I'm going to do time.net.ps1, and this is running the work stealing version of the code. We are not doing the display a little bit at a time to the console, because writing to the console slows things down. If you want like bonus tip that you can just go back to your office and implement straight away, go to all your ASP.NET Core applications, go to the startup bit of it where you are in your program, and this is running very, very slowly, and I don't know why. And builder.logging.configureLogging and add a line at the start of that that says clear providers, because that will remove the console logger, and you will see a roughly 20% speed up in terms of latency or requests per second or whatever else is going on. You just suck. Let's do native and see if that's any better. So this is building a release version, and then you see it's got this ILC compile and link native, and we have our code that's gone out there. There we go. So we have gone from 2.5 minutes to 5 seconds. On my machine at home, which is a big desktop machine with an AMD 5950X, it went from 1.5 minutes to, I got it down to 1.85 seconds, which is insane. Less than 2 seconds to process and summarize 1 billion lines of data is pretty impressive. So yes, if you go to github.com/RendleLabs, you will find a lot of this code is on there somewhere. I am very sorry that I have run over by 5 minutes. Sorry to the next speaker who hates me because he's got to get his HDMI working. I hope that was helpful. I am around today and tomorrow. If you want to come and ask questions about anything, then please do come up. I love meeting new people. So yeah, thank you very much for your time and have a good day.